All right, thank you. It's an honor to speak in the same session with W.E. Today I'll talk about quantum imaging with the super resolution beyond the optical diffraction limit. I'll cover two main methods: scanning version and the wide field version of quantum microscopy. Now I'll talk about our recent work at the quantum classical interface. Our lab has been working on photoacoustic tomography for a few decades now. This technology has been commercialized. The beauty is that we break through the so-called optical diffusion limit, because the standard optical imaging has problem with scattering, multiple scattering beyond one transport mean free path. It's very hard to achieve very high resolution. So we use diffuse photons combined with acoustic signals induced by the photoacoustic effect. We can achieve much higher resolution. So on a per dimension basis, we can resolve more than 100 pixels. This is an example. This was image from a live patient in vivo. You can see tiny blood vessels even without any contrast agent. We compare this using gadolinium contrast MRI. This is from the same patient. And the numbered arrows point to blood vessels imageable using both devices, but the lettered arrows point to vessels that are only imageable using photoacoustic imaging, so without any contrast agent. And so we can both see the tumor right here. In our modality, presumably we're seeing features due to angiogenesis, a hallmark of cancer. So that was sonic speed imaging. We're at the physical limit in terms of imaging. So within the acoustic arrival time, we acquire enough data for an image. So that's as fast as you can get, right? The minute you receive all the signals through acoustic propagation, you form an image. Can we extend it to light speed? It's 5 orders of magnitude faster now. So before this technology, it was not possible. You had to use pump probe. You cannot do it in real time. So that means if you want to have 100 time frames, you have to image 100 times. That's far less than real time. So this is the first time that we're able to get light speed imaging. As soon as the photons arrive, you got an image. And so at 100 billion frames per second, you can see a light pulse propagating in real time without repeating this event. So we've, over the years, we've accelerated the speed by another 3 orders of magnitude. Now we're talking about hundreds of trillions frames per second. But today I'll not focus on this. Both technologies have covered our classical imaging. At some point, we have to go beyond the classical limit. So now, in fact, this work motivated us to get into the quantum realm because this is the first time you get X, Y, and T at light speed. So if there's any entanglement, if there's any spooky action, we may actually have a chance to capture that. And that's how we said, let's work on quantum imaging or some even fundamental physics. There's this incredibly useful feature in entanglement. If you have 2 photons, if these 2 photons are independent, you have a product state, then you're subject to this so-called Heisenberg-like inequality. It's not exactly Heisenberg inequality, but they look like that uncertainty relation. So this Y difference and the P sum, they're not conjugate. So in other words, they're not subject to the uncertainty relation. In fact, if you have entanglement, you'll see this product can be tiny. And this is the EPR effect. In fact, the ratio between the right-hand side, the 2 right-hand side numbers, is the degree of paradox, right? And so if it's a 1, then that's the product state. If you have entanglement, then you can get something far greater than 1. And you can do the same type of measurement on both axes, and you take the geometric mean. This number is called a Schmidt number. And this translates into the degree of entanglement, or essentially the effective number of entangled mode pairs. And so this is very useful because eventually your super resolution imaging will be limited by this number. Of course, if you want to go beyond, get higher, that means you have to try to improve your source and try to build a higher Schumann number for super resolution imaging. Let's talk about the scanning version of imaging. We start with the pump beam going through the BBO to generate the entangled photon pairs. Let's look at a signal arm only. The signal arm is, if you look at a signal arm only alone, this is almost like a diffuse light illumination. We illuminate this object. It's like a wide field type illumination. And then we have a objective, and we have this essentially an effective pinhole for single photon detection. And so this is more like a point scanning imaging, but only the imaging optics provides spatial resolution. The illumination side does not. All right, so if you capture this photon on only one side, you get a classical image. But of course, we have this idler photon. We send it through a similar imaging system. We have another pinhole-like detector, and so that gives you the second photon. We do coincidence to get quantum imaging. Now, to understand the basic principle, let's look at this simplified diagram where we can treat this BBO as effectively a mirror. For this purpose, it's a pretty good mirror, but sometimes it's more complex than that. And so now we can time reverse this process. And so you have this pinhole now, it was a detector, now it's treated as a source at this moment. And so you can map this pinhole through this mirror, through this objective, onto the object plane. Now you have a virtual pinhole on the object plane. Now you got two pinholes working on the same plane. So that means this is a confocal system. And this is a classical confocal setup. And so you have a point focus on the object plane from the illumination side, as well as the detection side. And you will have a PSF squared effect due to the confocal detection. So this is a busy slide. Let's look at the key components here. That you can see this illustration of this entanglement pinhole effect due to coincidence detection. And we can also add polarization analyzers to detect birefringence. And so this can get quite interesting as well. This is a demonstration of a mouse brain slice. You can see the enhancement in resolution. And you can look at line plots. If you were to quantify this, you will observe roughly a square root of 2 enhancement in spatial resolution as expected. Now, an ancillary benefit is suppression of stray light, because stray photons are uncorrelated. Entangled photons are correlated. And so you can see here this classical image, if you have lots of stray light, it gets very spotty, but the quantum image cleans up all those stray photons. For polarization demonstration, so alpha is the polarization angle of the signal arm, and beta is the idler arm. And so in those 4 images, we only change the idler polarizer angle. Of course, if you look at only the classical images, nothing changes. So they look identical. But if you look at the coincidence quantum images, they are different because we're changing the idler arm's polarization angle. Through those 4 images, you can analyze and figure out the principal axis angle, the amount of birefringence or phase retardation. So you can offer measurement about the polarization property. We can also implement this using wide field version. Let's look at the key components. You have, we actually convert from the original source plane to the momentum space. So this is the source Fourier plane. We use that, map it onto the object plane for imaging. So on this side, this is where we place the sample as the object plane. In either arm, we have the reference plane. And a new feature in this design is that the 2 arms are entirely symmetric. This turned out to be quite important for us. So we relay this through an intermediate plane to the final detection plane. Another key difference is we use EMCCD. So you got many, many pixels working in parallel. The downside is with the first generation, when we have single photon counting modules, we have nanosecond temporal resolution. So we can literally detect coincidence with typically 8 nanosecond coincidence window. But the EMCCD will not respond that fast. It doesn't have that kind of temporal resolution. So you got typical frame rates, maybe about 100 hertz on that order. So we have to do something very differently in order to detect coincidence. This is one example frame. You will see like 2 halves. One half represents the signal arm, the other idle arm. We capture many frames. Then we look at covariance. Between unpaired pixels, you will detect a very low covariance. But between correlated pixels, you will see a much higher covariance for obvious reasons, because the photons are correlated in those positions. So we need to build an algorithm to figure all that out. We were inspired by the earlier works, but we want to do a little better. So this is a simple model. You got the left side and the right side between the 2 arms. This I coin is a coincidence true signal count, but you always have noise. You need to figure out the true signal. So we ran the covariance. You can write down the covariance equations. Now it turned out the noise covariance is negligible. So this is good news. We can recover approximately the signal variance. As we know, for Poisson distribution, the variance is equal to the mean. So this allows us to recover the mean. That's exactly the coincidence count we want. And this algorithm works better in our detection condition by 1.5 or 2.6x relative to the previous algorithms. Now we can use this to form images. This is a demonstration. We can improve the spatial resolution by a factor of 2 relative to the classic resolution. So we're plotting the resolution versus the axial locations. And if you look at the lowest points, you will gain about a factor of 2 using this kind of scheme. Again, as a bonus, we get straight light resistance. So here you got 8 times stronger than your signal light. So this is a pretty strong straight light. So the classical image doesn't really look good at all, but our quantum image can recover the features we want. We can even push it to over 100 times stronger straight light. Again, you can recover using the quantum imaging method. This is an image of a cell. Again, you will see the quantum image gives you much better spatial resolution. You can do a line plot and figure out the enhancement of the resolution. So even at a 2x spatial resolution enhancement, you can already find potential applications because you can achieve the benefit of UV without using UV light because you're gaining a 2x resolution enhancement using the quantum nature. So how does the theory work? Let's start with the classical PSF. This first equation is the classical PSF. This is related to the transverse wave number, which is the vector Q here. And R is the relative displacement from the geometric focus. This tells you how much blurring you're dealing with. For a circular pupil, you would get a Sambarrow function. Okay, so from here, you can figure out the diffraction limit. Now, what's interesting is in quantum imaging, with the symmetric optics that we use for the wide field system, you have this joint wave function, which is an entangled state. So this delta function links the 2 photons in terms of the transverse angular momentum. So without this delta function, you get a product state. In fact, sometimes if you mess up this entanglement, you reduce yourself to the product state. So here we take advantage of this delta function. And you can easily convert this integral into this integral. And now it gets interesting because you got this R1 prime minus R2 prime. We use anti-symmetric coincidence detection. So R1 prime is equal to minus R2 prime. You plug all that in here, you will get this factor 2 in the exponent. And so this means you will get essentially the classical PSF except with 2R in argument. And so this allows us to get 2x enhancement in spatial resolution. Now, if this delta function doesn't exist, again, you will come to a product state, then you will get a classical PSF squared. And so here's a quick comparison. So this is the classical version, but if you have a disrupted momentum correlation, you will get a classical PSF squared. That will give you a square root of 2 enhancement. One simple way to think about it, if you approximate your classical PSF as a Gaussian distribution, when you square a Gaussian distribution, you will narrow your distribution by root 2. But if you maintain the momentum correlation, you get this 2R as the argument. So that allows you to have a 2x resolution enhancement. So you can, even when you use entanglement, you may achieve different versions. Now, coming back to the birefringence measurement, let's imagine we want to image the birefringence property of an outer space object. That could be a light year away, so it's really, really far. If we were to use classical methods, we need to change the polarization state of the source and the analyzer angle of the detector using one arm here. And because it's so far away, it'll be very inefficient to control the source. The round trip time could be really long. And so there's a challenge there. But if you use entangled photon pairs, all you have to do is to have an entangled photon source. You just beam pairs to your ground stations. And all you have to do is to change your analyzer angles, alpha and beta, like what we did. And so the interesting part is you can actually perform birefringence measurement, right? All you have to do is to use coincidence detection. Now, if you were to compare this quantum scheme with the classical method, there's this spook action, essentially, because the minute you change station 2's analyzer angle, you effectively change the source polarization angle. So that's kind of pretty hard to understand if you compare quantum with the classical, right? And that actually motivated us to come back to some of the fundamentals, because really to understand this problem better, this entanglement is very mysterious. We almost have to understand the wave function collapse a little bit better as well. And so when we look at this fundamental problem, first we found out there's this equivalence of Bloch equation and quantum equation, Schrödinger equation or von Neumann equation. And that was stated by Majorana very early on. Majorana published this paper in an obscure journal, that's an Italian journal, right? Probably, I don't know how many people read it. In 1932, he stated the rotation angle alpha of the electron spin can be calculated both with a classical equation and a quantum mechanical equation. Now, at the time, the Bloch equation did not exist, but he actually wrote down this equation. He did not name this as any equation, he just called them classical equations. But it turned out this is the spherical coordinate form of the Bloch equation. You know, I'm pretty sure Bloch didn't know this paper, right? And in fact, Majorana, after he published this paper in 32, 6 years later, he disappeared. Right? So there were no conferences like this at the time, probably. Anyway, so Bloch basically rediscovered the equations, and we've been naming this after Bloch. So I actually suggest we rename the Bloch equation as Majorana block equation. So then Majorana went ahead. He didn't derive from the block equation to the Schrödinger equation. He said you can switch now to the Schrödinger equation. I suspect he actually converted but didn't publish it. So I said, well, I need to do it now. Do his homework, all right? And so it turned out it was pretty easy to derive. I start from the Majorana block equation, the classical equation. It's essentially the Newton's second law in a rotational system. And gamma is the geometric ratio, mu is the magnetic moment, B is the B field. I will use a unit vector n for simplicity here. So this is still the same equation. The next step is the key. I will use this Pauli vector, which is a mathematical tool. In fact, the Pauli vector predated Pauli. So he was the one who popularized this for quantum mechanics. But you can use it to represent any vector. You're essentially converting an R3 vector into a complex space representation. So we're allowed to right multiply the Pauli vector to this block equation, right? The one above right here. There's this mathematical identity that allows us to convert this cross product into dot product. Now the commutator appears. So this starts to look like quantum mechanics now. All right, here's the dot form of the block equation. I use color code to signify different types of quantities. If we define a density matrix using the red quantity, right, that's basically your vector direction. N is the vector of mu direction. And we can define Hamiltonian, which depends on the B field. Now we can get the von Neumann equation, which is quantum. In fact, you can go further and convert the von Neumann equation into the Schrödinger equation. Now, this whole derivation is bijective. You can go backwards step by step as well. So this gets quite interesting. Now, very recently, we found this derivation can be further extended to higher spins. So we just posted this on arXiv a few weeks ago. The derivation is very much analogous. So here you do have a higher spin. We use S to represent the spin operator. Right. Now you can similarly convert this cross product to dot product. And you also see a commutator. You can define the Hamiltonian. Now you need to define this dimensionless projection first as an intermediate step. So you don't really define the density operator right away. But you get an equation that looks like the von Neumann equation, but not really quite for the density operator. But the density operator, it turned out we can use a polynomial of this dimensionless projector to represent. So we can prove this in detail. Then in the end, you will get a von Neumann equation. So now we're projecting this to a higher spin, any spin. There's a caveat. This derivation for higher spin is only applicable to coherent states. Coherent states is a particular set of pure states that are constructed to mimic classical behaviors as much as possible. These are the two examples, the lowest spin examples. For spin half and spin 1, you can see the coherent states. On the right-hand side, you can see they're both represented by only two real numbers, real variables, theta and phi. Right? This is because the coherent state rays are homeomorphic to the two-sphere. Now, if you look at a complex projective space of all the pure state space, for spin S, the real dimension is 4s, but for S2, of course, the real dimension is 2, so they're not necessarily equal. So from the classical vector, we don't really have full access to the entire pure state space, with the exception of spin half. But spin half is so important because that's the foundation for qubits. For spin half, pure states and coherent states are synonymous. So that means the classical approach is equivalent, right, to the entire pure state space. Okay. So we can discuss more later about what's going on here. Then with that, we say we start to examine some additional problems. Stern and Gerlach, after they published their paper, Einstein and Heisenberg proposed this multi-stage Stern-Gerlach experiment. So the first stage is a polarizer, the middle one is a polarization rotation, and the third stage is analyzer. And they changed the wire current, basically changed the amount of rotation in the middle stage. They got something that's not expected. You will see the circles are the experimental data. They actually went down, but none of the existing theories will predict that downward trend. So they will all plateau. And so we use this standard hyperfine coupling. We got this better result than the previous versions because nowadays we have computer. We can solve this numerically, but still doesn't go downward. And so we're still looking for a better Hamiltonian to fix this problem. I understand we started a couple of minutes late, right? So, all right, so while we're looking for a better Hamiltonian, we started building an alternative theory with a postulate that the nuclear spin is very weakly perturbed because you can see here the geometric ratios, there are 4 orders of magnitude difference between the electrons and the nucleus. And we focus on the magnetic moment of the electron, which is the principal quantum of interest. So that's a strong measurement. We generalize the Pauli exclusion principle such that the nuclear magnetic moment determines the collapse direction of the electron moment. So there are 2 different situations you can see here. This movie demonstrates the precession frequency difference. So using this method, we got an incredibly good match with the experimental data. Right? We'll not get into the details of the equation here. We're not using any free parameters. There's no fitting. The R squared is very high. The p-value is less than 1 ppm. So that's the probability that the theory matches the experiment sheerly by chance. So that's very unlikely. But of course, we're at the mercy of this old data set, and we decide to run our own experiment. This has been funded by Julian Schwinger Foundation to pursue the experiment. So now we're back to a single stage measurement. We drive the magnetic field gradient to a very low level. Now we have a better way to resolve all those tiny amount of shift. The circles are from our own experiment. The dashed line is from the most recent standard collapse theory published last year. So it doesn't quite match with our experimental data, but using our own theory, we can match quite well. And so this is kind of a prospective test because when we developed the theory, this data set, experimental data set, did not exist. So there are a number of papers. If you're interested in details, please take a look on our lab's website. I do want to thank my own institution, CalTech, for building me a dream lab. This is one of the floors of our lab. We do have openings for students and postdocs. Credit goes to the lab members. We're mainly funded by NIH. We got some funding from NSF and CZI as well. And there are a couple books for details of some of the work. I will probably just leave them here for you to read while we have questions. Thank you.
Thank you for the very interesting talk. I kind of have 2 questions. So the first question is when people talk about the super resolution, right? There are kind of 2 kind of resolution people talk about. One is when you have enough light, it's just limited by your optics, your aperture. And the other is when you don't have enough light, it's also limited by the number of photons you observe. So in the super resolution you talk about here, are you talking about the one that's surpasses the photon number limit?
We assume we got enough photons.
Okay, yeah, that's what I feel.
But another quantum advantage potentially is subshot noise, as Warwick talked about, right? So that's harder to achieve. It's harder to have a major impact right away. For super resolution imaging, you already have a factor of 2.
Okay.
But with better detectors, because quantum efficiency is a major limiting factor currently. When you reach a higher quantum efficiency, you can potentially go far below the shot noise. And that's really another very exciting direction waiting to happen, but we're waiting for the right detectors.
Yeah, thank you. So my second question is, in the conventional ghost imaging, we are talking, we think about, we focus the beam down so that we get a very tight K vector correlation, and sort of the spatial vector correlation comes from the far field of the K vector, which usually doesn't perform very well. So in your scheme, I didn't fully capture. When you generate the photon pair, do you focus down your beam to something tight, or do you use a wide field to illuminate your crystal to generate the photon pair?
There are different ways of implementing this. You can do what people call the far field, and that's actually you work on the Fourier plane. You use that to illuminate your object. You can also do, sometimes you call I like to call that real space mapping, or sometimes people call that near field, but near field is really an overloaded term. Basically, you just map your BBO source plane to the object plane directly, and the image there as well. And so you can use either the original space correlation or use the K-vector correlation. You can use either one. In fact, they are Fourier related. But in standard ghost imaging, the signal arm has no spatial resolution at all. And so the resolution comes 100% from the idler arm. But what we want to do is we start with a best effort classical imaging system. So you already have resolution. You want to improve further. And so this is why we push this by another factor of 2, which is the Heisenberg limit. Yeah. Thank you.
Yep. Yeah, thanks. Thanks for the great talk. I just had maybe I was a little fast going through the latter part of your talk. I just want to understand, is so there you have some sort of higher dimensional wave function that's evolving according to that Hamiltonian, or is there something beyond kind of Hamiltonian dynamics that you're?
Are you talking about the higher spin?
I'm talking about the when you were this co-quantum.
Oh, I see.
Yeah.
Yeah. So there you basically have the electron spin. You do have the hyperfine coupling, right? That's the key here. So I didn't have time to talk about the exact equations of motion. We started because for spin half, in fact, for coherent states, as we demonstrated, the Bloch equation and the von Neumann equation are 100% equivalent. Yes. So you can use either one to modify further. So we just need to introduce the wave function collapse mechanism, because for a standard Stern-Gerlach, you are doing a quantum measurement. You get either spin up or down, mainly due to the electron spin, because it's like orders of magnitude stronger than the nuclear counterpart in terms of the magnetic moment. Once we introduce generalize the Pauli exclusion principle, we can figure out which direction the electromagnetic moment will collapse to, either up or down, right? So that depends on the relative angles between the mu e and the mu n. And so that's the extra term we introduced to quantify the process. So because within such a short time, it's very hard to explain everything with equations. So
okay, yeah. Let's thank Lihong again.
Thank you.